You got something for me? You got something for me, right? Specify, so that would be it's not like the toner is so dark that's leaking through. I guess. For college students.
We only had enough paper printed on single-sided, so. Yeah.
Okay, so let's talk about the article. Let's see if I can find this. Same. Hi.
I don't know where my copy of it went. I did print it.
It's not the time to talk about it.
Okay.
Okay, so let's talk about it. So I have some specific questions, but let's just get your reactions, general comments first. So what did you think about the article? Did you like it? What did you like about it?
I like that how it talked about, even though like the show and tell, like there's a big difference between show and tell and actually like calling kids up in a certain way where one solution kind of leads off into the next and kind of builds the concept.
Okay. So all right.
I really liked it. When they first went through the Fusion A, I was like, so what are they going to talk about? That sounded like a really good example to me.
Okay.
And then as they built off that, oh, well, these are all these different ideas of incorporating and how you can improve that discussion from just, oh, these are all the different ways you can solve this problem to, now there's a mathematical idea, and these are the students who can build upon that so we can start talking more about the math behind this rather than, oh, look at the 7 different ways we solve this problem.
Okay. Awesome.
I really like that it reiterated that it's not a quick fix for teaching a lesson, that it's a process, and because a lot of the articles just kind of say, do this is really important, but it doesn't.
Or it seemed to imply that.
Yeah, or it just implies that you can just tomorrow go in and start
Right.
teaching that way, and this one really drove home that it's not a quick fix, and it's going to take process, and you have to reflect and improve and polish your teaching.
Right.
But I did like how, in the sense that it was saying that it's not a quick fix, it did kind of give a framework of how to get it to operate in the classroom, what the overall look of it should be by the end result.
So they gave you a strategy.
Yeah, versus articles that kind of say, hey, this works, but they don't really go into detail on how to
How would you do it? Yeah. Other general comments? Tori.
I have my head on the bottom.
Anybody? Is there something else you want to
I
say?
had one
Sure.
I guess, kind of negative thing is that it seemed like it repeated itself constantly throughout the whole
Okay.
article.
Well, you better know it.
Yeah.
Okay, so what were the specific problems with show and tell that it brought out? So, what were some of the specific things it said? Yeah, Crystal.
It didn't allow the teachers to check if the showing and telling had helped the students who didn't understand. There was no way for them to assess if those 2 kids who didn't get it right, if they had figured out why they didn't get it right or any of that kind of stuff.
Okay. Alex.
It was not sequenced to bring about greater mathematical understanding.
Okay.
It was just kind of like whoever wants to go first goes first.
Yeah. Okay.
Yeah, and at the end, like specifically the vignette, but in general, it was all of these examples, all of these methods will work every time. It's kind of the takeaway that students should learn. But really, what they should have done is seen the strengths and weaknesses of each before they moved on.
Right. So it was give students opportunity to present, but little else.
Yeah.
Other comments about show and tell?
When he was choosing for show and tell, he only chose people who got right answers, rather than looking at, okay, well, now this person made a very common mistake, let's have them present their work, and so we can say, okay, now this is the common mistake, and why doesn't this work, and talk about the math behind that, so they can address those issues that other students might be having.
Yep. Tori?
He didn't really have people like explain a different path that they could have taken. He was just like, well, how'd you get it? And then they'd explain it, and he would be like, okay, cool, and then we'd move on to the next person instead of being like, well, how else could you have done it to really get them like thinking about multiple ways.
Yes, sir.
He like could have used that time to compare the processes that the students had used. Saying, well, okay, these two scaled up for this one used proportions and whatnot. So you can sit there and go, you can use different concepts to get to the same answer. And what situation would we use these in?
So that's a good thing about it.
No.
No.
That's what he could have done.
I could have done. I see. Okay. Zach, were you raising your hand or no?
A while ago, but
Okay.
All of my things were
Okay. All right. So, what did it say about effectively preparing to anticipate? What did it say that strategies for anticipating? Let's go with.
Well, you can't give students work that you haven't previously gone through yourself,
Okay.
like multiple times. Multiple topics. Yeah.
So you got to do the problem yourself first. Alfredo.
He also said I can think of incorrect ways to solve it.
Okay.
So you can be prepared to correct any misconceptions that the student might have.
Okay.
That's what I was gonna say.
Okay.
Yeah.
Sorry.
It said that it was like important when you're first trying it to maybe focus a lot more on like the first two phases instead of all five, and then like the next time, like focus on the first three and like slowly incorporate all of them, but to like ease into it a little bit, because if you try and do it all at once, you won't pay the proper attention to the first couple steps.
Good. What else? Crystal.
You could research, there's lots of research on like where students learn and have misunderstandings, so you could just like Google and stuff like that to figure out where they might mess up or not understand something.
Yeah. Sorry.
Talk with colleagues about misconceptions that their students have had or that they've had at some point with it too.
What I found is the best tool for anticipating is having done it once before. And so like as I teach these courses semester after semester, certain courses, like I begin to recognize where their thinking goes wrong, and so that helps me to. I mean, even if I'm not using this framework, it just helps me to kind of preempt that. Say, here, this is what you might be thinking, and so we want to. So I adjust the way I talk about it because I have an idea of where there might go wrong.
I have a similar experience. I'm a student teaching now, so when there's like some classwork, I'll walk around and just kind of see what the students are doing. If they have a question, I try and keep that in my head.
Right.
And as I'm like going over examples, like I'll ask the question about that specific, maybe incorrect way of doing something, and then we'll have like discussions on like why we should have done something another way, or kind of basically what the article said, anticipate your students' questions.
Right. Yeah, Laura.
I think that's convenient for us in a high school setting because we may teach like 4 of the same classes, like 4 different hours. So as the day progresses, I mean, ideally you should be learning from each hour and progressively getting better, whether you're using this way or just using little parts of it.
So, anticipation exercise. Asking students to make meaning of, say, this. Here's your anticipation exercise. Do you anticipate that calculational, non-conceptual thinkers will do?
What's the function?
Dr. Elna,
What's that?
Dr. Elna.
Okay, kind of. Michael,
Find the answer for f of 2.
f of 2, right? F of 2. So this is very common, right? So they think that f of 5 minus f of 3 is f of 2. When it's really a matter of, so that's just showing that they're not looking at meaning, right? So if we talk about the meaning of this and the meaning of this, what would we find? Comparing those meanings.
Well,
Or-
the top one, you're looking at a change between the two output values when you're given an input of 5 and you're given an input of 3.
right.
But the other one, you're just talking about, okay, when your input's 2, this is the output that you're going to get.
Right, so it's a totally different meaning, right? So they'll have totally different meanings. And so a student that says that those are equal is just not even going there in terms of thinking about what these expressions mean, right? Okay, cool. Let's see. So what are the roles and tasks during monitoring? What did it say about the roles and tasks during monitoring?
The teacher? The teacher?
The teacher. Teachers, yeah.
When you're monitoring, you shouldn't just check for correctness of their answers,
Okay.
but you should check for their thinking behind why they're doing what they're doing. So ask probing questions to say, now why are you trying this? Why are you thinking that?
Right. Tyler.
To evaluate like which groups are like hitting concepts that you're trying to teach.
Okay.
Maybe particular focus and hone in on them and see the way that they're doing it, like just getting as much information, but also looking at the students that are doing it wrong. So depending on how you do sequence them, you could, just knowing what the common misconceptions are, like paying attention to those, but then also making sure that they're rooted in fundamental concepts behind the lesson, so that when you pick them, what you're trying to accomplish can be accomplished for the teacher.
Right, so we want them to do it their own way and think about other ways of doing it, but at the same time we may have a goal of how we want to shape their thinking and have a certain way, that we want them to appreciate and understand. So, right. What else? Monitoring phase, Chelsea.
If you monitor them while they're working through it, or you'll have more time to prepare yourself for the discussion and how you want it to guide all those different concepts that the kids are going to bring in. You'll have more time to think about how I want that order, or how am I going to weave that into back to my goal of portions or something like that.
Okay. So you're starting to talk about selecting, right? And sequencing. So what are the sequencing techniques that they talked about? Yeah, Molly.
There were a few. I guess the one that stuck out to me the most was looking at a few of the of the processes that people went through that were incorrect, and then kind of weaving that into this is where you had some misconceptions, and turning it into here are some different ways that people solved it. What are the connections between them, and what are the underlying mathematical concepts?
So when you sequence, you're connecting the ones that were off base with right along with
Right.
this kind of the same strategy but correct.
Mm-hmm. Yeah.
Other sequencing techniques.
They have to
There you go.
sequence them from basic to more complex.
Okay.
So start off easier so the students that had trouble with it can actually see the easier strategy or the more basic strategy, and then move on to the other more complex strategy that the students use.
Yeah, Jack.
You want to do similar ones closer together so that you can compare and contrast why this one is slightly different and how they both come out to similar answers.
Okay. Tyler.
If you're sequencing, you might want to address the most common way to solve the problem first. The students can have their ideas validated before going into a more unique or more obscure way of solving the problem.
So that's in kind of a little bit in contrast to easiest to most difficult, right? So most common first rather than least complex first. Those might not be the same thing. Yeah, Crystal.
We do least efficient to most efficient.
Okay. Ooh, yeah, I like that.
I like the one that first they cleared up. They looked at the ones the most commonly used methods that were wrong, to like let those students know that like to understand why they were wrong and like open their minds up for the future discussions. That they if we don't address that, sometimes the students are like look at the other ones but still think theirs is like would work, you know, or I don't know. I like that you clear up some confusion first before you try to build any concepts they have. Since what they know was what they try to do was incorrect.
Okay.
So you can clear their palette before you try to build anything on it, whichever other way you decide to do it.
Mm-hmm. Okay, and so then you may have, you know, kind of your opinion of what you would, right? So those are different. Those are not. You can't do all of those, right? You have to choose. So, what about the connecting phase? What were some of the strategies in that? Carla, I haven't heard from you yet.
That's the last phase, right? The
Yeah.
connecting phase. That one, I think I cut. Well, you have to make sure that the key ideas that you were thinking throughout the process and throughout the students presenting, that they're now clear and you can discuss them with the class. So you don't want those key ideas to be like not understood by the students. That's kind of what I got out of that one.
So putting a focus on the key ideas.
Yeah. And closing them.
What else? Lee, anything about? Do you remember about the connecting phase?
I think it was mentioned earlier that you want to connect their responses to each other and contrast them or between them, or just whether they're next to each other or the first and the last. To make sure that they realize that there's a string that goes through all of them, and that way they can see where they're different and how they're similar.
So it's super dependent on the sequencing phase. What you're saying that there's this coherence to it, right? To the sequence. All right. So they put up this. Any more comments about the individual phases? So did you think about why did they make the picture, this diagram of the phases the way they did? So just if you didn't think about it, I want to just give everyone a second to think about it before someone talks. So why did they make this diagram the way that they did? Why did they form this visual in the way that they did? Okay, how about Daniel?
Each ring, as it grows out, is dependent on the previous rings.
Uh-huh.
So how well you monitor is dependent on how you anticipated the student responses and how you anticipated the lesson going. How you select student responses, how you monitor, or is dependent on how you monitor your students, and how you sequence through it depends on how you select them. So whether you're doing easiest to hardest, most common to least common, it depends on how you select the students, and then connecting it depends on how you sequence it. So it's just like a scaffolding or stairs or however you want to do it. Is one is dependent on the other. You can't take the next step without fully understanding the previous step or fully committing to the previous step.
So there's several of you had your hands up. Do you want to add to that? Or? Tyler? No?
If you don't place equal importance on all of them, then it's just going to fall apart. Like, you're going to anticipate really well, you can monitor really well, but as soon as you are, if you aren't as good at selecting one day, you're not going to be able to sequence them in a way that you're going to be able to connect them to the, and it all stems from anticipating, but anywhere in there, if you don't monitor well, if you get a phone call during it, then you're not going to be able to select. You may, if it's in the middle of the semester, then you may know that this group usually has good ideas in this one. You might be able to wing it, but the whole point of this is so you don't wing it.
Cool.
I see it as you have to have the overall concept in mind during all of the steps in order to know how to anticipate, but also how to eventually connect everything.
Cool. Yeah, so it's about dependence, right? Each one is dependent, absolutely dependent, for success on the previous one. So it includes it, right? Each one, and that's what you guys were saying. So what was meant by authority and accountability of the students in the classroom? So what do they mean by authority? Is this, Alex?
You want to define one or the other?
Whatever you feel like.
So with authority, I felt like it was kind of, it meant more like to a certain degree expertise. So it's like how good the students, because they describe the students as being in authority on particular subjects. So it's like if math, if they're discussing some topic, students may be more likely to ask one particular student for help on that. And then the other thing with authority is they also describe how the teachers have to be careful not to undermine student authority, because we don't want the students to give answers based on what they think the teacher wants, and instead the students should give answers they think are correct. And then I think accountability was accountability to like the overall math standards and knowing what goals you wanted the students to shoot for, and not having any accountability kind of makes it so it can break from like traditional math norms or something like that.
Okay. Yeah,
I think the authority part also kind of made sure to have the students feel ownership over their work and their conclusions, so that they don't just say, hey, this is how math works, but instead they figure it out and feel some sort of attachment or pride that they were able to figure it out.
Okay. Yeah, Crystal?
I feel like what you said, it's more like, I feel like if you give students kind of free rein, a lot of times, especially like in my internship, if I were to just give them a problem and be like, go at it, they're gonna feel like kind of like, I don't know what to do, no one's, like, I need someone to tell me what to do. And so just having kids have that like empowerment, like I can discover this myself, I can, think mathematically to learn new things. It's not, I don't have to always be told things, And then I think accountability is knowing that like, that they are, responsible for what they're saying, and that needs to be, their reasoning needs to be correct and sound, and if it's not, they need to be able to revise it and understand that you're not always going to be right, but you're accountable for your own ideas.
Yeah, so how are these like a polarity, right? It's kind of like it's like a scale. On one side, there's high authority, and the other side, and low accountability. And the other side, there's high accountability and low authority. So how can it be described that way? Seeing them together like that. Would you agree with that? That there are like a one versus the other, and this is kind of like you can go too far into authority, not enough into accountability, and the other way around. So how is that true?
I feel like maybe if there's too much authority of the students in the discussion, that they're not going to have that accountability of learning the material that is required of them. And so if they're just running the discussion and not really pulling in those key points from the teacher, then they're going nowhere in the objective that needs to be met.
Right.
But on the other hand, if there's no authority by the students, then they just feel that the teacher is the say-so and the teacher is controlling the whole thing, and they don't have really freedom to discuss their ideas and feel valued in the classroom.
Right. Spoon feeding, right? Like,
yeah.
Or just direct instruction, passive learning, right? You just information. You're just gathering information rather than a creative, investigative process in mathematics. Because it's in the discovery, it's in the investigation that learning occurs, right? Yeah, so there's this balance between the two. So, in terms of like the last two articles, kind of comparing them or speaking about one or the other, can you imagine yourself implementing this in the classroom? And maybe one more than the other, or what does that look like to you? Do you envision yourself teaching with some of these frameworks? Comments about that? Were you going to say something? Yeah.
I was agreeing that I can see myself doing it, but I think with the previous articles, it kind of scared me a little bit because I thought my own math knowledge is not deep enough where it needs to be. And like big picture wise, like whatever class I happen to be teaching, do I know what they need to know where that fits into the big picture of their whole math education? And so I didn't feel as comfortable and confident, but a little more reading this last article made me feel like, okay, I can start at the bottom and I don't have to be perfect in the first couple of years. It'll take me a couple of years to be able to get to a level where I want to be, but I can do it. So.
That's really important. So this article gave you like a little hope.
Yeah, it did. It gave me a little
That's good.
confidence.
No, that's key. That's absolutely key.
Oh, I was going to say that I would just pull key elements from each one and kind of like create my own like mash of these, just like the little things that I liked and little things I feel like I could really implement in my own classroom.
I feel that they almost kind of go hand in hand with each other because the article before this was probing all of these questions to develop this lesson protocol plan that you had, where some of those questions go into anticipating your students' responses. So where if you're building in that protocol, say a classroom discussion, this fits right in with it. So
she's talking about something that this article kind of emphasized, or that the first article didn't as much, which is someone. So what was that? So what kind of the overall point of this? Yeah,
I thought we talked more about the selecting and sequencing.
What's that?
I feel like this article talked a lot more about selecting and sequencing
Okay.
than the other ones. The other ones talked about looking at the possible student responses, monitoring the individual and group work, and then bringing it into a class discussion.
Okay.
They conveyed that. This one also conveyed that, but it stressed the importance of like setting up the class discussion. Where the other ones did hint that it's going to take you a while to become excellent discussion facilitators, and being able to lead the discussion is going to be hard. Whereas this one gave you tools like writing things down and other things, and then selecting the exact questions and then picking which way you want to go about it. You can change it up. I felt like this one helped you set up the discussion more. Kind of give you tools. So I'm not saying you have to do it this way, but it definitely introduced some tools into it.
Felt more practical a little bit.
Yeah, the other ones it had the same ideas. This one just broke it down more.
Would you say that this one was more about the teacher being more attentive to the students' thinking? Would you agree with that? And that's kind of what I was getting at. That this article is really all about listening to the students and having their thinking be a huge factor in the way that you teach and how you move along in the process of teaching this thing that you want to teach, right? So the students' thinking and how they're conceiving it and what they're doing in grappling with it, then is part of this building process of you teaching them, right? Other comments? Okay, so let's pick up where we left off. Was this the points I gave you? Anyway, these are the new points. Same idea. I was like, I think I can get different points last time.
yeah.
All right, but anyway, so here we go. So did you think about what this next command line is going to do? And did you not peek and cheat? Oh, good. Good, honest class. So let's just kind of, so maybe at your table, just kind of get yourself up to speed with what this question. So again, if you want to repeat a point many times, you can assign it a parameter, and then just graph that point, and you just Put the parameter. So now what I'm doing is I'm saying 1 minus t times a plus t times b. And what is the role of t in graphing calculator? What's the role of t? How does it treat it? How would you describe the role of t? Yeah.
A parameter that ranges from 0 to 1.
Okay. So a parameter that ranges from 0 to 1. Does it have to be from 0 to 1?
No, whatever
you select. And so does it take those values one at a time, or does it take them all at once, or what will it do with t? Like as opposed to n, right? So how's n different than t? Tyler?
T is just set as a range.
What's that?
T set as a range from 0 to 1.
Okay.
And whereas n can be a range, but it only takes on a particular value at a given time.
Okay.
Whereas this one takes on all the values all the time.
Okay. Similar to, what's that similar to in graphing calculator? Something that's taking on all the values at once.
X and Y.
Yeah, x and y, right? So like when we graph x and y, so x is, it's like spraying all the x values into whatever command line that you put at once, thinking of them as all these x values on the x-axis placed into whatever command line you have. Same with y. Okay, so t is similar to that. But it doesn't have, in the xy plane, it doesn't have an axis, right? It doesn't have, it's not, you don't see it explicitly. But it has kind of the same function as x and y. It will take on all those values, or puts in all those values simultaneously in whatever range that you have it set at. Okay, so now we're going to set t from 0 to 1, and we created this statement. 1 minus t times the point A plus t times the point B. Or actually, not the point. The point is the location, so it would be 1 minus t times the coordinates of A plus t times the coordinates of B. So maybe just now, just talk at your table where your current thinking is on this. We're just have a discussion. Where's your current thinking about making sense of what, when I turn that on, what are we going to see? Okay, go.
So awesome. Like when t is 0, 1, and then like maybe some min.
So
like
Don't cheat. Don't do it.
So at 0 you're in A, and at 1 you're in B. Where you at? Because it's 0.5 for A and 0.5 for B.
every change
Yeah, because 0.5 is easily cut. So directly in half, you're not going to be like merge and then merge. Like you're going to have a straight line. Because half way between A and halfway between B is like halfway between A and
well, what's 1 minus 1? Now we got that, right? Plus 0
Yeah, the max point A in the lowest.
Use
So
or
somehow,
sure.
we know, since we said like for example 0, then we're gonna have we obviously have to connect our it's gonna start at point A and then an apple. So we just don't know what's gonna happen. So this is not a straight line. Because when I go
I don't think it is.
It's a long thing.
Well, that's what does A represent?
Like the investigation took 1 hour.
So what happens if this is 2? What if having 2 is 2? Then it's going to be negative A.
Well, I mean, yeah. I just seen that.
Yeah, I don't think
I wanted to like plug in.
Oh wait, just
Yeah.
Oh.
See what's the pattern.
But that's why I was like,
and also
if you're manipulating it too much,
I'm sure later on you're gonna like fix it in a way that
like, and then you add
it makes it like a straight line.
and then,
It's like Subway sauce.
Unless you're gonna fix
we went to China.
Every time
I'm sorry, we discussed it's basically some names like last week, but it's straight line.
You guys
We just looked at it at 0 and A, and then I get to make sure that it's getting on like a curve and it's still like it's
zero, two, one, and
that was our discussion. Aww.
why? So that's so you guys talking about this?
That's just really great.
Yeah.
Do you know how much that was? What's
I always try to remember.
That's so weird.
If I was honest, I had my dad read something.
exactly, that's an hour of your life.
Like some like heavy assignment, so.
I'm not got A minus T times A. So then, so you go A minus T A plus T.
Yeah, but you took out
I imagined a line like
Because it's still A minus.
oh shoot, I didn't see that.
A minus.
That's five equals one half, so
What do you want to do?
I assume would be
A plus T was 0.
I think it's gonna be like a like between
so it's about half of this and half of this and half of this. So we did half of the x coordinate and half of the y coordinate, so order is in point.
okay, but then you would also do
Zero is
A x coordinate, half of the b x coordinate.
What? Just because say?
Yeah, so
Zero
if
is just the line.
Yeah.
So you start with A, and then you're subtracting T times whatever. So if you subtract, so T is 0, right? You plug in 0, that's gonna make all of these
And frankly,
0,
we'll just
right?
follow
So it all just goes away. So you still have A minus 0.
Okay.
So it's always gonna be
Yeah, exactly.
A minus 0, so it can't be less
Like,
So in fact, what
So whatever is happening is always going to start with A. So then if you have A plus
oh,
You're
it's
right.
not even
You're
0
right.
and 1.
together, yeah, so if you're multiplying them, or if you're adding them, it's always going to be kind of way.
Okay, so there's different ways to reason about this. So what was your reasoning? Here's some different tables reasoning about why it's a line. You all suspected it was a line. Why is it a line?
We plugged in a 0 value and then we plugged in a 1 value. And so at 0 you're at A and at 1 for T you're at B.
Okay, so
And then we took some midway point, so like 0.5, and then we plugged it in terms of that. So we figured out that would be halfway between and just kind of did it that way, like reasoned with it.
okay, so what I heard is you took t equals 1/2. And when
Yeah.
you took t equals 1/2, where did you go there from there with t equals 1/2?
So in T equals 1/2 you have half of your coordinates, or half of A and half of B, and you add those together to get your midway point.
A is a
You're so
Coordinate
taking
pairs.
like half of A of X and half of B of X,
okay.
and adding those X's.
All right, so
You get a
taking
new
half
X.
of the X, half of 3, and
Yeah.
half of 7, and adding them.
Right.
And so what does that accomplish? How does that help?
It helped us like figure out that like it wasn't going to be a curve, so it wasn't some point like out here. It was some point right in the middle.
Right in the middle. Other thoughts about taking half of 3 and half of 7 and adding it together? What does it give you?
5.
You get 5, okay? So what's going on there?
Well, that would be a new x value, and you have to do it again for your y values to
Okay.
get that, to get a new point.
And what'd you get for the y value? 2, right?
Yeah.
So you get the point 5, 2. So what just happened? Right? So when t equals a half, you got the point 5, 2.
We just found a point. Like it looks like in a t value, you found a point that was in between those 2 points.
Is this in between them?
No.
Is this in between them? So what do you mean? So we gotta make the connection now to reasoning that this is going to be a line. So where's the connection? We get the point 5, 2. How does that? Why does that point say, oh, this is looking like it's going to be a line? Tori.
Well, because when you plugged it in, it was like, for the 3 and the 7, it ended up at 5, which is like directly in the middle of both of them. And then for -1 and 5, it ended up at 2, which is also directly in the middle of both the points. And then we did it again for 1/4, and then like 3/4, and the same thing happened where it was like close, or it was like 1/4 of the way between 3
Okay,
and 7.
so let's fine tune our language here. So the point 2, the point 5, 2. She talked about the x coordinate being directly in the middle, and the y coordinate being directly in the middle.
I think it has to do also, you could find the rate of change between the points, and you know it's going to be a line.
Did you do that? Were you finding rates of change?
Did I do that?
Yeah.
No, but
So let's talk about this point 5, 2. Let's really nail it down. Why is this helping us determine that we're going to get a line? Yeah, Michael.
It's in the path of the shortest distance between those 2 points.
Okay, shortest distance. Other thoughts?
For equal changes away from A, it moves that much closer to B. So it's like keeping a constant relationship, or vice versa.
Okay.
Moving halfway from A is the same as moving halfway from B on the
Okay.
same line.
That's true. That's true.
Yeah.
You guys have that? No. So 5, 2 comes from the. So can we be a little more mathematical than directly in the middle? That's right, directly in the middle. But what is 5, 2?
Midpoint.
Midpoint, right? It's the midpoint. It's the midpoint of these two, and the midpoint comes from taking the average of the x values and the average of the y values. So when t is 1/2, it produces the midpoint of these, which is on the line, right? The midpoint is on the line. So this is a lot of evidence that we're doing that. And so then we investigate something like, well, point 1. So how can we say point 1 is going to be on t equals point 1? That point would be on the line. So this is maybe now what Daniel was talking about. So this is where I kind of reformed this. And when you do the math, you get a plus t times b minus a. And so we want to think about t equals 0.1. Now remember, a and b are points. They're a pair of coordinates, right? A and b are a pair of coordinates. So t equals 0.1. So I want you to just, using this form, a plus t times b minus a, and t equals 0.1, convince yourself that that resulting point would be on the line. Okay? Go. So look at this particular form of that, this rearranged form, and work on t equals 0.1, and come up with some good, convincing mathematical reason why the resulting point would be on the line. Okay? So mini investigation. Go. what is this doing, right? So we're looking for meaning and purpose in this form of it. What is it? What happens when you do that?
Okay, so what is B minus A? B minus A. Right, you're going up the chain. From A, you're going up. Because you're taking from B minus A.
You guys are so close.
B coordinates. Subtracting from how many?
This was this what I just kind of presented. You gotta track it.
Yeah, it's finding where you're going. There, so A plus the change creating one of. Point. Yeah. And I think it creates change
Okay, so you got the right overall idea, but this is your conception of B minus A. What is B minus A? So separate it out.
That's right, but that's why I would think that's
I mean, it definitely. The idea of
No, you're looking at a linear relationship. Is the reason. Yeah. I think it's that's how you justify it.
broken up into the coordinates, right? Okay, so what does B minus A mean? What is B minus A? Can we represent that not with numbers but with symbols? What is that? What's the meaning of that? Did you guys come up with that? The coordinates of that are like the change in x. Which change in x and which change in y? So how could we represent delta x on this picture? We're starting from where, Tyler?
Starting from point A.
Is this A down here?
Yeah.
Okay.
And since t is equal to 0.1, we would only go a tenth of that actual distance.
Okay.
And then the change in y would go from our horizontal line up to point B.
Okay.
And since t is 0.1, we would only actually go up a tenth of that distance.
What does this have to do with what I showed you last time in class? Remember what I showed you at the beginning of class last time? That animation that I made? Yeah, so what does this have to do with that? Remember what the point of that was? Okay, which was about what? What's that? No, it's nothing to do with circles.
Oh, that one.
Yeah, the bar.
Okay.
Yeah, so let's say more. So constant rate of change, right? But
For equal changes in x, there's equal changes in y.
okay,
Even
so
though they're not equal to each other, they're still it's a constant.
For every change in x.
so I don't remember if the part that I showed you. Did the part that I showed you talk about this? Did we talk about relative size? Is that in that discussion? Relative size?
I don't think so.
It wasn't.
Was that on Tuesday?
Yeah.
I'm like so like counting days.
So anyway, it was showing that, there was these two things, and then let's see. And it was showing that, so this is delta y, and those were increasing in length together, but the relative size was being maintained. The size of delta y relative to delta x was maintained, and what was the value? Remember? 1/2, right? And that would be the ratio, right? So this is like measuring delta y in the units of delta x. It's like measuring. That's what quotient does. Because relative size is measuring your numerator quantity in the units of the denominator quantity. So how does this picture demonstrate that? Versus
That maintains that relative size.
so what does? Be more specific, Michael.
So that tiny triangle,
Yep.
the change in x is the change in y is equivalent to the large triangle, the change in x, the change in y.
Right. The size of delta y relative to delta x is the same in the big triangle and the small triangle. And what is that size? What is that relative size in this case? Was it?
No, it's I think isn't it 6 to 4 to 6 or something?
What is the relative size in this case of delta y with respect to delta x? 3/2, 6 to 4, 1.5. Delta y is 1.5 times always delta x. So you can take both of them. If you multiply both of them by 0.1, that relative size is maintained, right? So what does that have to do with a line?
Sorry, say that again.
What does that have to do with convincing us that we get a line? Please.
Since its rate of change is constant, it's a line.
Okay.
You could think of it like having infinitely little triangles being drawn, and just like the tip of the height is like a point, and it's just gonna, since the ratios are gonna be the same, it's gonna like follow it up to the next one.
Okay. Right. So yeah, since the relative size of this vertical is the same relative to the horizontal, you just have this like locus of triangles, and the points follow a straight path, right? But points follow a straight path because that delta y is staying consistently the same relative to its current delta x. This is going to follow. Okay. So what do we say? Notice that. What about? So we said in this case, it's the relative size is 1.5, right? What do you notice in this picture when you look at this picture? Thinking of the number of 1.5, maybe thinking more in terms of slope, right? Is that a slope of 1.5? Yes or no? Does it look like a slope of 1.5?
Doesn't look like it,
So what?
The scale's off.
What's that?
The scaling is off.
Scaling is off.
So it looks kind of like 1.
It looks like more like what we think of 1, right? So can you judge a slope by its steepness?
No.
Yeah. So we shouldn't. So what I'm getting at is we shouldn't have an image that 1.5 should look a certain way, because all I have to do is what? Okay. What about the steepness now? Is the steepness 1.5? What's the slope now? Slope is 1.5. So this is this idea of shape thinking. Students use shape thinking all the time. That the slope is a measure of the steepness of a line. It doesn't work. You can't have that construct because steepness can change and the slope stays the same. So slope means constant rate of change. Always means constant rate of change, but it can't be thought of as steepness. Okay, anyway, so that was just for free. You didn't have to pay me for that one. Okay, so I want to show you this. I have function f of x, 1/4 x squared plus 5. G of x equals 4 cosine of x. And I have the command line 1 minus n times g of x plus n times f of x. And I'm going to set my n sliders to slide from 0 to 1. Again, don't do it. Don't do it. Don't cheat. What's going to happen as I slide n from 0 to 1? Talk about it. This is just g of x. I'm not graphing this thing, okay? This is just g of x. What will happen when I'm going to slide the slider starting at n equals 0, and I'm going to slide it to 1. What will the result be? That's what you're going to start with the slider. I'm going to turn it on. The slider is going to be at 0. I'm going to slide this slider from 0 to 1.
In this case, it's kind of 4. So 4. We're pointing to 0. Yeah. Why?
But you don't just have a gradually in the position, so you have have some kind of like so it's gonna start and go up here, but then the exact closing will be out here, right? So there's some kind of like it's according to it's gonna be scaled bigger than whatever. I'm not sure what the shade's gonna look like. Does that make sense? Someone just because I talk about values, so I have to like think like, what are we actually doing this? What is that?
Okay, so when I turn it on, what's going to happen? So I'm going to turn it on now, n equals 0. I'm going to turn on n. What will you see? I'm just going to turn on n. Lee wants g. Okay, so n equals 0, you get g. Did everyone predict that?
Yes.
So now what's going to happen when I increase n? So okay, so let's predict. I want to hear what you think.
Well,
For small values of n, let's say for small values of n, what's
going to happen is you're going to still have your cosine curve, but your amplitude is going to start to go down. So the mounds are going to get smaller the higher n goes, and the tops of the mounds are going to get further apart, as well as you're going to be adding a portion of the parabola to it. So the further out as n you go, the further up the cosine graph is going to shift. So it's going to start decreasing in height, decreasing in amplitude and spreading out, as well as further away from the origin, your sides are going to come up. And that's going to keep happening and happening and happening until you get 1 when it's just going to be the parabola. So it's going to like stretch the cosine curve, make it smaller, and then be the parabola.
wow,
That was very thorough.
it's thorough and confident. Anyone top that? So let's look at some of the details of what he said, if you agree. So there's point 4. That's point 4. 0.8. And what will happen at 1?
It'll be
Less.
1. Okay, so I'm trying to demonstrate this is a very powerful mapping technique. It can be used in all kinds of settings. So we saw it, what were the first entities that we had? Points, right? We used it with points. And by using this mapping technique and letting t go from 0 to 1, so in that case we use t, right? So what did we get? We got all the points on the line between them, right? So we got a mapping from the values 0 to 1 to what? So it was a mapping from all the values from 0 to 1 of t mapped to what when we did the first thing? Right? So think about this as about this as a function or a mapping. T, right? So 0, 0.1, 0.15. Think I'll have enough room? 0.7, whatever. You know, all the numbers from 0 and 1, right? Map to what? What did it map to? Each one of these mapped to what? I heard a point and I heard a coordinate. Each value t mapped to a coordinate. Is that right? Before. No. Each t value mapped gave us what? Point, a pair of coordinates, right? Each t value mapped to a pair of coordinates, a point on the line. 0.1 mapped to this point that was 1/10 of the way in x and 1/10 of the way in y from A to B, right? What do we get? And what about in this one? So in the first thing that we used, we got points. What about now? What does each value of t map to now? N?
Oh, are you saying in the new solution with the sine curve or the cosine curve, what is n map to now?
Yeah, so n. It'd be n now. So we use n instead, right? Thank you. What does each value of n map to? A graph? A graph is a representation of what it maps to. A function, right? So each n value is mapping to a whole function. Okay? So and there's other things you can do. So like for instance, let's see. Here's a function, okay? So I'm going to graph this function. How do I graph this function? She likes it. It makes her laugh. If I want to graph up this function, what do I do on graphing? Y equals f of x. Okay. I don't want to use y equals f of x. I want to graph it a different way. Something that we've learned. How can I graph it a different way?
You can use
Parametrically. So you do it. You graph this parametrically. I want you to use it. Write a command line that will use a parametric approach to functions to graph this function.
How much can you do? X to the minus x cubed.
So do you want to have like,
Option B. Victor.
I saw another one that was like R's.
What do we have on R?
That's on the
Oh, let's say we give T the value.
Graph it parametrically.
Oh, all that? Oh, you want to I think that's the same thing. Just, I mean, thinking like that, just fucking
Everyone got it? So I'll put the graph up there just the normal way. Your job is to have it be in parametric form. Show me parametric curves. What are parametric functions about? Last time. What are parametric functions about? If you know that, then you know what to do. What are they about? Gotta remember.
I guess it's part of it.
What happened?
When it's going from 0 to 1, what's that?
Why?
Because that's what T says.
Got it.
So then change
But he doesn't want us to change this.
It's okay for now. I mean, you got the idea. You got the idea.
Oh, okay.
Good job. So what is a parametric function? What is it about?
So we made a coordinate.
Okay, remember, what does this do indirectly that a parametric function does directly? What does this do indirectly that a parametric function does directly? That was what we talked about.
I'm sorry.
That's good. What does it do? What is a parametric function about?
Yeah, I think it would. But I think it's I think it's supposed to be
How do you
That's taking
A.
how to do it this way.
No, that's actually
It's only cutting off everyone else.
right. Let's see.
There. That gives you that.
Because you say T is
This is what parametrics is about. This is what parametric functions are about. Remember, they directly give you define curves by the points described by their coordinates, right? One point at a time by their coordinates. X coordinate, Y coordinate. This makes a graph, but it's not in that same framework, right? So it's more indirect in that your input is the X coordinate and then it cranks out an output, which is the Y coordinate. But parametric functions are about calculating each coordinate separately. They're kind of on equal ground, right? So you get them all separately. So how are we going to graph this? So we can put equals and do it again, right? So x equals, how we're going to define what the x coordinate is. Y equals, define what the y coordinate is of each point. But we want to show all the points at once. So what are we going to put in there? What for x? T. F of t. I don't know. That's a good question. Why didn't I put y? Oh, because I didn't. I see. What happened? All right. So now here's this is part of your homework. Think about how can I graph a wider range than 0 to 1, leaving t from 0 to 1. So I want to leave t as it is from 0 to 1, and I want this same. I want to graph a wider range. Say I desire to graph from -8 to 8, like that. How can I use a parametric form of the equation to show this graph from -8 to 8 while leaving t goes from 0 to 1? So just think about it. I'll give you a hint. Use an important tool that we were learning in this class, okay? So it's part of your homework. So leaving t step, t is going to go from 0 to 1, but we want this to graph a different range than from 0 to 1.
Is that on our homework for Tuesday or is it?
Yeah, it's part of your homework already, yeah.
That's fine.